The final type of paleoclimate archive that we'll explore today are ice cores, and these can be used to reconstruct components of atmospheric climate, including air temperature and atmospheric composition. Similar to sediment cores, ice cores contain layers of accumulated snow and ice that track changes in climate over time. Ice cores can be taken from polar regions as well as from high altitude regions, such as glaciers on mountains. And there are various proxies that we can measure in ice cores to reconstruct different climate variables. For example, paleoclimate records of surface air temperature can be made by measuring oxygen-hydrogen isotopes of ice cores. We can also reconstruct changes in greenhouse gas atmospheric concentrations by measuring the air bubbles preserved in the ice. And a final example is a reconstruction of atmospheric dust flux, which can be measured by reconstructing and measuring changes in the dust layers that are preserved in ice cores. And here's an example of these three paleoclimate reconstructions over the past 800,000 years, with changes in temperature on the top, changes in atmospheric CO2 concentration in the middle, and the dust flux on the bottom. We already discussed a bit about oxygen isotopes when we were looking at marine climate proxies. But in this tutorial, we'll be looking at a hydrogen isotope record from ice cores. So, what are hydrogen isotopes and how do they record temperature in ice cores? The two most common hydrogen isotopes are hydrogen, which is the lighter isotope, and deuterium, which is the heavier isotope. And this ratio is referred to as delta D, and the units are per mil. So the ratio of this light and heavy hydrogen isotope changes in the ocean during warm and cold climate periods, and this change occurs as a result of ice volume variations. So, for example, let's take a look at cold climate periods. Seawater evaporates and the light isotopes preferentially goes into the water vapor. So during cold periods, when ice sheets are larger, more of that light isotope gets trapped in the ice. So the ice has more of the light isotope compared to the ocean. Therefore, the hydrogen isotopes of the ice itself is more depleted overall. In contrast, during warm periods, ice volume decreases as the ice melts, which releases that trapped light oxygen or hydrogen isotopes back into the seawater. As a result, the ice has less of the light isotope compared to the seawater, so the delta D of the ice would be more enriched. So the overall takeaway is that in colder climates, there's a more depleted delta D in the ice cores, and in warmer climates, there's a more enriched delta D of the ice cores. Delta D and delta 18O allow for long-term reconstructions of temperature from ice cores. Shown here are examples of ice cores from Antarctica and Greenland that extend back 800,000 years. On the top are examples of hydrogen isotope records from two different Antarctica cores, and on the bottom are oxygen isotope reconstructions from two different Greenland cores. And on the x-axis, present day is on the left, and the past 140,000 years is on the right. And you can see that this y-axis is delta 18O and delta 2H, or delta D. And these record changes in temperature with these more enriched isotopic signatures indicating warmer climates and the more depleted indicating cooler climates. In this tutorial, we'll explore a delta D and atmospheric CO2 reconstruction from the Epicodone Sea ice core. And during this tutorial, we'll plot delta D and CO2 records and compare them, and we'll assess changes in temperature and atmospheric greenhouse gas concentrations over the past 800,000 years.